All right. So, ordered pair notations and column vector notations to represent a position vector. What does that mean? Suppose I have a point P up here. Its coordinates are x and y. I mean, yes, it could actually be anywhere on the plane, right? Not just in the first quadrant. I'm going to go from the origin to that point, and that's called the position vector of P. And normally I shouldn't have used P, because then I can't make my point. I'm going to use capital A instead, because we call that little a is, and we would normally go x, y. Actually, this syllabus is different. It's using a round bracket. It's equally valid, Ryan. It is actually a 2x1 matrix. You can write this as x, y, perfectly fine. That's, I think, what I'm used to doing. What does the textbook do? Yeah, the textbook uses square brackets.
What does my syllabus use? Oh,
You've got your dot points. What does it say?
I have no points.
You had the dot points up a moment ago. Algebra doesn't say anything useful at all, does it? Yeah. So that's the thing. They didn't define there.
Yeah.
So this syllabus, the new syllabus specifically says round brackets. I'm going to do this a lot. All my hard questions use square brackets, because that's just what I'm used to.
Is it actually matrix?
It's a 2x1 matrix, correct.
But do we actually treat it as a matrix?
Most of the time, no. But there are some times when you will. Yeah, it is really a matrix. They also say you can also write this coordinates also effectively is the same as the position vector. Right? Technically, I'd go, this is an ordered pair and this is a vector. The textbook uses square brackets. I will do this a lot. I'm going to try and change to round brackets because the new syllabus says round brackets. I won't get it right. Why do I not like round brackets? You just learnt this notation for something else. Choose. Technically, choose is like this, and a vector is like that. Are you going to get that neat distinction under stress in an exam? No. I like square brackets myself, but you know, the syllabus is the only thing that matters. So we're going to try and use round brackets. If I want to know the length of A, or the magnitude of A, well, how do I find the length of this line? Pythagoras, right? X squared plus y squared, and get the square root. And that's the rule that's up there. How do I find this angle to get the direction?
Sine O. Wait, what do we have?
So stop and think before you speak. You can use any of the tree if you've got this length.
Yeah.
Because you've got this, I'll get another colour. You've got this and you've got that. Right? So length is this squared plus this squared square root. To get the direction, I could use any of the trig. Why is one better than the other two?
Because less calculations.
Which means what?
Less working out.
I'm not interested in how much working out there is.
Simpler to understand when you read it.
If I have to calculate something, I might make a mistake. So I would far rather use the two numbers in the question than my own calculated number.
Oh, yeah.
So I would go, this angle is the inverse tan of y on x, because tan means I'm using the numbers from the question and not something I have to calculate. If I made a mistake here, this doesn't rely on that to get the direction.
Yeah.
Be careful. When we get into Unit 2, we'll start talking very seriously about tan positive, tan negative. How do I work around this? Just be careful with this. Which angle you're finding. If you get a negative, it's down here. If you've got a point up here, your tan is actually going to be negative, and you have to think, oh, it's actually this angle and I want this one. So just be careful. Ryan, think principal argument.
Yeah.
This is basic complex numbers.
Okay.
It's just polar form versus Cartesian form. This is Cartesian form.
Yeah.
Okay? That's Cartesian form. Putting these two together would be polar form.
Yeah.
So I can describe a vector either way. So you can write the same vector in two ways. You can write it like this. This is Cartesian coordinates or rectangular form. Or you can write it as length and direction.
Do we need to know that for this though?
You will. Polar form is here. And then when we get to 3D, you actually need length and two directions. So you will have to do it and convert back and forth. I will wait a little bit until they talk about that before we get to it.
So polar form needs to come back.
Yes, and this time in 3 dimensions. But complex numbers was only in 2.
Yeah.
Okay? So you can talk about polar form, just means length and direction, or you can talk about rectangular or Cartesian form, talks about the coordinates. So how do I suppose I have a vector, let me do the same things. Scalar multiple. Suppose I have 3 lots of, I'll try and use round brackets, 7, -1. So that was what we did before, scalar multiple of another vector. How do I work that out?
3 times 7, 3 times -1.
Yeah, that's all you have to do. Because I'm going 3 times as far across and 3 times as far down. It's exactly the same. It's meant to be a nice round bracket. That's all you have to do for a scalar multiple. What about adding and subtracting? So suppose I want to add 2, -1, and 3, 4.
Can you do it Cartesian?
Can you?
Or can you draw one?
So what we have to do is go back to the definition, right?
Visualizing it.
Exactly. Think about it. Where do I do this? I will do it here. So 2, -1 is this vector, and 3, 4 is this vector. If I'm going to add them, I'm going to take this and stick it on the end of that. And I want that result. Well, how do I get up here? I go down to here and I go across this far and up that far. I really am just adding these coordinates to the coordinates I already had. So I can just go 2 and 3 is 5, -1 and 4 is 3. And you are allowed to do that. How do I know? Go back to the definition, vector addition. Take one and stick it on the end of the other. Subtraction is the same. You're just going to subtract here. Do I write one for you? Let's go 2, -1, -3, 4. If I'm subtracting it, all I'm going to do is go 2 -3, -1, take 4. That's all I have to do. And you can combine those. Multiply by scalar, relative position vectors, they do talk about that, don't they? I'm going to leave unit vector for the moment. We're not going to I and j until we have unit vectors. Then they do go to polar form. So yes, let's try some of that. I will actually talk a bit more about this. So, in that proof I just wrote for you before, I wrote AB with an arrow. And when we did that over here, to get from A to B, I can be more specific. Relative position vectors. This is important and worth writing down somewhere for notes. The vector AB is B minus A. Now I'm going to try and prove that to you. Where like this, little a is the vector from the origin to that point.
Huh? What's B?
If this is A,
Yep.
and this is B, right? I might make that even bigger. That's A and that's B. So
Oh.
let me show you.
So is B just from the origin to B?
That's little a,
Yeah, okay.
and that's little b. By convention, you don't always have to follow that, but if you're talking about position vectors, you just write the lowercase letter means from the origin to that point represented by those coordinates. This is a convention. Little a is the position vector of big A. It's just a convention. It helps us do things without having to explain ourselves every time. Now, think about the vector AB. To get from A to B, I could go negative A plus B. Negative A plus B. So the vector from point A to point B is the position vector of the finish minus the position vector of the start. So for example, if P is, let me use something other than P, let me go, C is the point 3, 1, and D is the point -2, 8. What is the vector CD? What is the vector that takes me from C to D? Well, you go, that is little d minus little c, which is -2, 8 minus 3, 1. So the vector from C to D, opposite order, is -2 take 3 is -5, 8 take 1 is 7. And this is the vector that goes from C to D.